Log on, tune in, find out. Another good idea from Cambridge.
So the first speaker this morning is Paul Horja from the Oklahoma State University, and he's talking about categorical matrix factorization.
All right. Thanks a lot for the opportunity to speak here. So what I want to talk about today is some work in progress about categorical matrix factorizations, well, matrix factorizations as you'll see, and also about, just to draw your attention, since I draw the attention of some people in the audience who might be interested, about some work in progress also with Borisov, which some of it appeared on the archive, and which might be interesting for mirror symmetry, and I'll try to justify why is that interesting for mirror symmetry. So there is a connection between the two. The second part has something to do with categorical resolutions, which of course people want to construct. So okay, so let me start with matrix factorization. So let me give first some motivation. So I should say that the title, of course, is I'm not sure if it was so well chosen. Everything is categorical, after all, about matrix factorizations. So the motivation that I will try to show here has to do with the various instances where we've seen matrix factorizations show up in various versions. So I'm bound here to not to mention, of course, everything. So I just made my kind of pick of topics, if you want. So of course this story started with Eisenbud, Buchweiss, Knörer, and many, Van Straten, and again. And then in some sense was picked up more recently by Kontsevich and Orlov. So so I will kind of course, try to the main thing about the first part will be try to put Orlov's work into a context which I think, as I said, might be interesting. So so what Orlov is doing, and actually that is really what Eisenbud was doing. So they look at categories of matrix factorization. So I'll be very sloppy here. I'll just want to emphasize the differences between the various approaches. So the objects are things like this. Where the PIs are oh, yeah, I should I should say what the case I'm talking about. So I'm looking at really at the affine case. Right. So PIs are finitely generated modules, free modules over B, and the P0, P1 is P1, P0 is some W, where W is some regular function like that. So, and then of course there is the whole yoga, which I'm going to review here, about how to define the categories. So this is, again, this basically is what Eisenbud did. Then Orlov inspired by the physicist, in fact, and I'm going to say a bit more about this too. So, defined the graded matrix factorizations. So in this context, he worked over some graded ring, graded algebra, semi-simple. That's actually quite important in that story. And yeah, and in fact, his point of view was not, in this case, you can assume, we don't have to assume that the algebra is commutative. And then homogeneous element of some degree d, which is in the center, right? And then for this, he defined the category as follows. So let me be careful here. So there is this shift in the grading of these modules. So the PIs are finally generate projective modules here. And the condition then is that right. And then, of course, again, you do all the yoga and you construct the DG category associated, and you construct the matrix factorizations. I'll mention that. But N is
D.
Sorry?
N is D. D equals N, I think.
Yes. Very good. Of degree N. Then, more recently, that is a few months ago, in fact, I think, Polishchuk and Weintraub wrote a very nice paper which is kind of, again, foundational in some sense. And, you know, there are various discussions there about the various contexts, but you know, if I just say a few things about what they do, I would say, let's say they start with an algebraic stack, a line bundle on it, a section, and their matrix factorizations look like this. And the conditions are the analogouses. So we sort of start to see the pattern in this construction. There is the shift in Orlov's approach is replaced here by this twist by a line bundle. And then finally, this, in some sense, the most interesting example, I think, which mathematically I believe is still a bit mysterious, at least to me, are these constructions in physics by Horja, Walker, and a big paper by Herbst, Horja, and Page, which are actually, I think, very powerful. And then there is, I think, also a paper by Herbst and Walker, where they actually encode in this category of matrix factorization the so-called R charge. And so I don't want to go over the whole story here, and maybe I should also add here Aspinwall. I don't want to go, but fundamentally, at least as an example, just so that we get some idea about what they have a multi-graded, as I said, this is the easiest case they consider, multi-graded ring where which you should think geometrically as the homogeneous coordinate ring of a toric variety. So it's graded by a finitely generated abelian group G. And then the R charge has to do with the fact that you add a 2Z grading on top of the kind of geometric one, such that the variables x have grading 0 and p has gains grading and in this story the degree of with respect to G of W would be 0, and clearly the degree with respect to P would be 2, right? And in this context then, so we look at, so if we want to actually think about these toric varieties as stacks, in fact, we have to look at what's called the irrelevant ideal. And for any graded module, graded A module M, one can look at the submodule of elements in M such that some power and so and then we say that M is a torsion if so this is kind of the so geometrically the torsion objects are going to be objects whose support is at the locus determined by the ideal. Can I have some water? No, I mean I can. And so these determine a category inside the graded modules over A, And the category of modules over the stack then would be exactly obtained as so the category of, if you want, coherent sheaves over the stack is going to be equivalent to the category of graded modules modulo this the torsion sheaf. So by the way, there is, and this might be relevant, there is some very nice, quite important work by Smith and Zhang about extending the usual Artin-Zhang construction in the non-commutative case, of course, to the multigraded, and it unfortunately hasn't appeared yet as far as I know, but I know there is, I have a version of it which is quite impressive. So they actually, all the necessary ingredients are there to work in actually in this context. So so then the matrix factorizations in this case would be so I'm going to call this shift by 2, the shift in the P grading, and so so my point is that there is, of course, all these constructions have something in common. It's not hard to see that. And moreover, in this case at least, the relevant categories that at least the physics tell us that we should look at, and I guess these categories are, in some sense, they go back to this old paper, well, older paper of Witten about n equals 2 phases. The category they consider is they do something like this. They take some matrix factorizations and then they quotient by the torsion. Although I think, and in fact, I mean, it's possible to do this, the more geometric approach would be to do this quotient by actually looking first at the geometrical object which coming from the stack, and then doing matrix factorizations here. So the point is that we would need to understand, that's where categorical, the title of my talk, that's where that comes in. We would need to understand what's a matrix factorization in the categorical context. So in the sense that, you know, we instead of just an algebra or something like that. So
I'm sorry.
yeah.
What do you mean by taking the quotient of matrix factorizations by torsion? You see, the objects in matrix factorization are projective, so there is no torsion there.
Right. Well, of course, what you do here is you actually define you show that this is equivalent to the singularity category, and then you quotient that one by torsion. So then that makes sense. So, but philosophically, that's what they're doing. So, right. So the category of singularity is there. You can certainly take the image of. You can project this category of torsion objects inside it, and then take the quotient by this. So that would be fine. But somehow, when you actually work through the computations, all the computations are done here in the category of matrix factorization. So, the other point I want to make is that if we believe in this, the fact that we would like to make sense of this notion as for matrix factorization where the underlying object is a category, that also is useful in the context of the problem I mentioned about trying to construct resolutions, Kreppen resolutions, and depending on your definition, you may actually get a categorical Kreppen resolution, which again is a category. And even if it's defined as some modules over an algebra, that algebra is so hard to work with that it's somewhat easier to work with a category. So I should also mention that there is actually important work by Positelski, which actually I have to say I was not aware while doing this work, and then until I met Orlov at some conference, and he told me about Positelski's work, which is it's similar in spirit to what I'm going to do, and in fact it might be the right approach. It's more complicated. So he works with sheaves of algebras, so over stacks or schemes. So, but as I said, I have not carefully read his papers. He has quite a few papers there. So, okay. So, so let me then move to the actual construction. So I want to define, as I said, the context, and the context, I think, the right context for all these is to consider, to start with an additive k-linear category with a monoidal weak z action. So I'll explain in a second what I'll write the definition. So what I'll write now is actually lifted from Drinfeld's paper on quotients of DG categories. I don't know the exact title. It's one of the appendices there. So so let C be a k-linear. So I'll start with an additive category, and then at some point I'll have to add more and more assumptions with, so this is Drinfeld's terminology, with a weak action of Z. So what he means by that is that there is a map from a monoidal natural transformation from the, a functor from the monoid Z to the categorous monoidal functor from C to C. So when the monoid Z that we're looking at, of course, is the one that you expect. And so under this map, M would go into a functor Fm, and Fm and Fn would satisfy the in particular we see there actually have to be automorphisms or equivalences rather So given this, in this context, I want to actually, here I have a bit of a notational problem, but so I want to define kind of the generalized the X groups, and then I want to think about the superpotential as a natural transformation between F0, F2, and of course everything now is in this context of monoidal categories. So we want to, there are a few compatibility things that have to happen. For example, Fn, for any F better. And then so you know, the usual. So basically, what the F's do, define a graded structure on the category, obviously. So now, the category of, is this maybe?
Cell phone, maybe.
No, I don't have a cell phone. Maybe I should move something. Maybe this works better. So, so we want to define it, the DG category N, whose objects are P, and lowercase p is a such that F1P P is the morphism corresponding to, maybe it got better. So.
It got better. It must be a mobile phone in the audience.
So, and then are actually and of course we define the differential as again the usual. Have to again be careful here a bit, but actually this can be right. Right, so one of them has to be F from I think this is P, this is Q. And of course, then one checks that so before we move on, let me show you how we can view all the previous examples, in fact, as special cases of this construction. So in the previous examples, fundamentally what we had in all cases, we actually did start with an additive categories, some additive categories with some monoidal structure, which is either in the here the monoidal structure is trivial. In the graded case is the shift of the grading. In this Polishchuk-Weintraub case is the twist by the line bundle. So so the example, if say A is additive with a weak action of Z, and let's call these guys Fn bar, then I'm claiming that if we define the following category of pairs, the usual, this is also very common, of course. So this is Fg. The only footwork we have to do is when we write the action of F1 would be F so basically it's the action of the F, the monoidal action on the category B, of course, depends on the F bars. What's important, though, is that even if Fn bars are trivial, the Fn's are not. So again, if you want, you can think about this as enhancing the group action, the underlying group action in the categories, and but it certainly this covers all the examples that I discussed earlier. And again, in fact, just to mention again, to make this clear, Positelski has this construction in a more general context. I'm not sure what the connection between them, the two constructions is. So, okay. So, so what do we do next? Again, we continue with this yoga that we usually do. So, now let's assume that A is abelian, and of course everything is, all the functors involved and everything is actually are exact functors now. By the way, I actually wrote this down. There is somewhere in this book by Kashiwara and Shapira, the new book on sheaves, I was quite amazed to discover that actually there is. They do a bit differently the construction of the derived category than one wants to, but at some point they actually have some exercises which they call these categories with translation. And just for those of you who are interested, they have some exercises which are, they're not quite that, but they're exercises about, you can give them an interpretation as exactly about superpotentials viewed as natural transformations, or even better, one of them actually, the second exercise, I think, lends itself to some kind of deformation of the superpotential, in fact. So I haven't checked that, but it's quite interesting. And yeah, so I asked actually Shapira if he knows where that comes from. He didn't remember where this exercise is from, so probably it's not from physics, but okay. So now, in order to make this more general, I want now to say that I take a category C, which is an exact subcategory Why am I doing this? I don't want to take just a billion subcategory. That would be too restrictive. For example, if we want to work with projective modules, those are they form an exact subcategory over a ring, not so now we want to apply the whole construction that I described to C. So I think I called it, I just called it M. It was not good, but in the previous notation, so this is the homotopy category. And Fn, of course, it turns out that this is a triangulated category. And Fn induce corresponding equivalences on however, as people nowadays know, of course, this, if we want to actually construct properly the matrix factorization, this is not going to be enough. We need to take one more quotient, and this again is something that essentially it goes back, I think, to in the DG context to the paper of also to this paper of Drinfeld, where he shows, and Keller, where they show how to construct the quotient. But it's explicitly done also by Positelski and Orlov, and so basically we need to take the quotient of by this thick subcategory generated by totalizations. And I'll just, for technical reason, I'll write you what this means in this context. So it means that basically, if we have an exact sequence like this, we associate the totalization and in this context looks like this P0, 0, 0, D0, P1, 0, 0, F minus 1, D1 P2. So so you, and again, you normally, if say if W is 0 and you want to construct the derived category, you'd have to invert quasi-isomorphisms. Here we don't have that luxury, so this is the construction that replaces that part of the construction. So so this, let's call it all right. So now in this context, in fact, one could try to reprove all these results and hopefully obtain generic proofs for all the, for example, all the Orlov's results. Unfortunately, it doesn't work that way completely. So there are some things in progress. So some things that I can do, some things that I cannot do. It's a matter of choosing the right approach. So let me just mention the connection with the category of singularities at the central fiber, as it were. So one thing one can prove, so more or less the goal from now on is to just maybe add some hypotheses and do diagram chasing, so that even Orlov would be happy to read these and wouldn't have to go through all the proofs every time he writes a paper. So as I said, that doesn't work quite that way, but sort of what makes it work is the following, that if one looks at so this would be then, as I said, just by abstract nonsense, one can prove this, which is, so this suggests to actually consider the category W, 0, let's call it, the full abelian subcategory of B, I think that was my category B, where the objects are exactly those objects P, and one issue that arose recently as I said, there are quite a lot of papers on this topic, and I cannot mention all of them, where people try to relate the category matrix factorizations with a version of this category W0, or rather of its derived category, right? So the question would be, what can we say there? And there are various contexts where there are complete results. So the result that I can prove is the following, that I need the following assumption, that assume that the natural functor let's call it I the lower star, has adjoints, left and right adjoints. So under this assumption then, the category so there is a fully faithful functor from this to actually
I'm sorry, what is B?
what is what?
What is this category B?
Yeah, B. A, I think I lost track of my A, B, and C's. I guess it's A, sorry. I should say, now, Orlov can prove this, since in this, this is kind of the bare hands approach where, as I said, the goal is to use just diagram chasing and try to go through Orlov's proofs, which many of them are diagram chasing. Orlov actually proves an equivalence in some cases here. But for that equivalence, one would need more assumptions. Then I think Positelski actually in his latest paper, which as I said I haven't read, actually he also proves an equivalence here. And I'm not sure about the relationship between his work and exactly this work, but it's a question mark. Yeah?
I understand. This category C name, it was not directly related to it, some subcategory, right? On the left-hand side.
Oh, I'm sorry. Yeah, so this should be.
What is this letter?
A. A is the ambient category. So these are generalized matrix factorizations, right? Where I think they're called in general coherent matrix factorizations. So, and these would be, this would correspond to the perfect.
And how do you define the functor? Which you claim to be fully free?
Well, the functor is exactly the co-kernel functor. So again, it's there's, you know, if you the thing that you have to show then of course is that it factorizes correctly with respect to all these quotients. And as I said, that under these assumptions, everything boils down to diagram chasing. So now, if, as I said, if in this context I can prove more than this, is an open question. So. Yeah.
Can we see the whole?
All right, so I want to say a few words, as I mentioned earlier, about this joint work with Borisov. This is quite different than.
I'm sorry, are you sure that you take the quotient with respect to the pullback of matrix factorizations, not with respect to pullbacks of?
Yes. Absolutely. these are so-called perfect complexes. So, right, so let me say a few words about this more. So the relation with this is that the hope, at least, is that perhaps if we have something, a category of coherent sheets on something very singular, and so this is joint with Borisov. So something very singular that one could take is what a Gorenstein toric singularity.
Are such things LCI?
Sorry?
Are such things locally complete intersections?
No. No, I'll write explicitly what they are. So they're only one, that's why they're good, because you know exactly what they are. They look like this. They're the spec of the ring associated with some semigroup to associate to a cone, and the cone is, so M is a lattice, K is a cone, and what's special about K is that K is the cone over a reflexive polytope included in the hyperplane in a hyperplane. So,
why reflective?
because that's kind of the Gorenstein condition.
The Gorenstein condition is in the hyperplane, and it should be in the dual. The dual cone should be the cone over a polytope, not the.
Right. Right, you're right. No, but that actually is true that the any Gorenstein singularity is of the form the spec of this with included in the hyperplane. That's a. But I still want to take it reflexive because I want to do mirror symmetry. So having a reflexive cone, which is called a reflexive Gorenstein cone, allows us to move to the dual lattice. So this is the dual reflexive polytope. And in some sense, we can get for free Kreppen resolution of this singularity, which is pretty bad in general. So in those Kreppen resolutions show up this way, right? You take vectors which include through the points of the integral points in the polytope, which include at least the boundary, and then you triangulate them. You consider simplices, and what you get, torically, you're going to get a smooth Deligne-Mumford stack associated to each triangulation sigma of the polytope. So, so if I call these stacks, then then this is a Kreppen resolution of that rig that Gorenstein singularity that I started with.
Which dimension is this story?
Sorry?
Which dimension is this story?
Well, if the lattice is dimension, you mean the dimension?
Dimension of singularity. I mean, any?
No, it's exactly the dimension of the lattice, right?
Yes, and do you take that to be arbitrary?
Sorry?
Do you take that to be arbitrary?
Yeah.
And do you assume that Kreppen resolutions exist?
No, I don't think they come for free here. They do exist. That's what I'm telling you.
Interesting.
I just retriangulate this, and the point is that this, this magic of toric geometry tells you that this is a Kreppen resolution of that Gorenstein singularity. Commutative, mind you.
In low dimension, this exists, but not always.
Sorry?
He's looking at special class.
No, but this is a Kreppen in the sense that, this generalized, this is actually going to be the lemma for stack in general. So it's not going to be a variety. So in that sense, is stacky, right? Maybe that's a word that is confusing to me. And of course, we know that in higher dimensions, you cannot achieve this in the world of varieties and all that. So our project, which has been going on for some time now, is to actually, we believe that, and there are some mirror symmetric reasons that I will not mention here, that we believe actually, and I'm sure it is related to spaces of stability conditions, that there should be some family, flat family of categories, which are all, in some good sense, Kreppen resolutions of very likely non-commutative resolutions. So, of course, the ultimate project is, in this very concrete example, can we build such a resolution? And, well, we don't know how to do it, but this is some old work I did with Boris, so we actually know something about that. So we know the parameters. Again, for mirror symmetric reasons, the parameters that this resolution should depend on have to do with the actual vertices in this triangulation, right? So it's a very naive point of view. There is some torus action going on there, but so the story that the diagram that we've had in our, I don't know, 5-year-old paper is something like this, right? That if you take these stacks, and you take a modification so here we have the Fourier-Mukai functors. Here, let's call this Fourier-Mukai. And the crux of the matter, what we hope to help us here, is that there are maps here from solutions to the Picard-Fuchs equations associated to the system or to the GKZ system at some point in the moduli space corresponding to this. And so this is all old stuff, but there was a problem here. So So since we want to do this functorially, so it's very important that everything is functorial. And the problem is that the GKZ system that is usually considered in mirror symmetry is bad, or in some cases. In other words, people who work in mirror symmetry know that sometimes you get more solutions than you need. So the generic answer, the sheaf of solutions has a rank equal to the volume of that polytope. In general, though, under various conditions, you're going to get more solutions. So it's always an issue. So even here, the issue is to cut down to find the right subspace so these actually hold. So in this piece of the puzzle, we actually can fix, and we fixed in this little paper that is on the archive with Lev, where in other words, we actually constructed the functorial version of the GKZ system, which we call the better behaved GKZ system. And it has the property that is under any circumstances, it always has the sheaf of solutions, always has the right rank. So
what do you mean by right rank?
The volume of this polytope. So so always the expected rank, let's say. Even the old GKZ generically has that, but there are this points where the rank jumps. And of course, this is a whole industry. Some people that I told about this who work on GKZ, in fact, got pretty unhappy because they make a living by studying exactly these points where the rank jumps. But our point is that, in fact, mirror symmetry should have been done using this better behaved GKZ. And let me just write it down, and it's very easy to write down. And of course, if you don't know anything about GKZ, that's not going to make any sense, but hopefully for the people who know, that will make some sense. So the modification, I don't know if so these are the vectors, what is usually called this set A, included in this, and we define our GKZ depends on, of course, n variables, and each solution is a set of functions indexed by the points in the cone, such that the following. So that we replace the first equations with this modification, and the second one has to be modified accordingly. So where mu is an element in the observation here is that phi 0 satisfies the classical GKZ. And in fact, we tried to actually construct a category using these functions. So in some sense, it looks likely that this category should have, one way or another, some transcendence embedded into it. And the transcendence, we believe, should come from this GKZ, mainly because it's kind of the only way that we sort of can move between the two sides in some sense at the level of moduli spaces. So and I'll finish by saying that we actually did this for not only for lattices here, but we also allowed some torsion. So for n with torsion, and then if n has order torsion 5, the solution space will have dimension 5 times the volume of the polytope. So the torsion always shows up like that. And all right, so I'll stop there. So thank you.
Are there any more questions?
What did the last third of the talk have to do with the first 3/4?
Well, the connection is that, as I said, if we want to, there are two steps of the same process, but the middle process is missing. So what we would like to do, we would like to construct matrix factorizations for use these categorical constructions for these categorical resolutions.
What's the category?
Well, so as I said, the hope here using this new GKZ is to be able to construct a flat family categories, right? Which at these limit points in the moduli space, they generate to these commutative resolutions. So give me one of these categories. Now I have a superpotential. I can certainly lift the superpotential to this category. And so I will need this construction of the matrix factorizations in the categorical context in order to make sense of what the LG category of V-branes is. So that's a connection, but as I said, in some sense, the most important link in the middle is missing. So if I...
Do you have a proof for the Olof's theorem for hypersurface in Torrey-Gorenstein Banach varieties? Like equivalence of categories between this matrix factorization and the...
No, I cannot do this in this context. It will not give me that. So there must be some smart hypothesis added for this, for the... Oh, so you're asking about this theorem with the categories?
Olof proves the hypersurface.
Oh, I see. Oh, the LG Calabi-Upper terms.
Yeah.
No, but yes, that's something that I'm looking at. Yes, that would be actually, of course, that's the most amazing thing in this physicist story. So, but I cannot do it at this point. So.
Okay, if there are no more questions, let's thank you for again.